I'm Ethan Almanza.
I'm Daniel Sanchez.
And I'm Justin Lambright, and we're the Benchwarmers. Go ahead.
And here you can see we have our regular imports, but we also added a third import, which is the math import, so we could use terms like pi and other things like that. Below that, we have all our inputs, our mass, which is the mass of the object, our initial velocity, which is the initial speed of the object, theta, which is the launch angle from with respect to the x-axis, and your r is your radius of the object, and eta stands for the viscosity of the fluid. And like I said, those are all inputs, so you can tweak the numbers and all that stuff. And under background here, we have sphere 1, which we programmed to have the radius and all that stuff. But the main deal is it has a green, we programmed it to have a green trail behind it. And for sphere 2, we programmed it to have a red trail behind it. And below that, we have t, which is, so before the calculation started, t is set at 0, and then your dt is the rate at which it makes new calculations, so it's every 10,000ths of a second. We set gravity equal to negative 9.8.
Oh, and the here we have FG, and it's in a vector form for force and times gravity. After that, we have the sphere of we have both of the spheres going across, and that's both of velocity in vector form. And the next 3 lines we're going to skip. I'll let Justin cover that because that's to do with air drag. And so now we go to the while loop. And as you see, the rate, 25,000 speed of, that's the speed of the frame, showing you the motion of the 2 spheres. And then on sphere 1 equals sphere 1 plus FG, that's in 2 vectors added together to
Component-wise.
for the component-wise. And then we had sphere 1, position 1 plus equals sphere 1 v times dt, which is the control movement along the path recalculated every 0.001 seconds. And then we got this next sphere 1 is point y is less than or equal to 0. If that's true, that means the while loop is gets broken out, and then we move on to the next one, which will be the t equals 0, right?
Yeah, set it t equals 0 before you start our next while loop for the red ball for air drag. So go ahead and scroll down. The rate's doubled to make it go a little bit faster. I don't know why. But up at the top of the page, it says initial velocity. We've set the initial velocity to just the regular one, how we always do it, by trig. Then set the final velocity, which is equal to the initial velocity plus the derivative of, or it's the force of drag divided by mass times the iterations per second, or how fast we calculate them. And then I put the force of drag as the initial velocity times Stokes' theorem, which is -6 pi eta r, and we calculate that every dt. So we do this as a calculation of iterations. That's why I'm setting initial velocities and final velocities. So when we go inside the while loop, we'll complete the calculation, then we'll reset the sphere 2.v to the final velocity, and then set that to the initial velocity. So the next times we go through the while loop, that will be the initial velocity to find the next final velocity. And then we'll reset the force of drag, since it is constantly changing through the path, to the new calculation for that iteration. The next part is so that the force of drag doesn't go in the opposite direction, so we don't want negative velocity in the x direction. So the if statement is saying that if the x component of sphere 2 is greater than or equal to 0, then keep doing what you're doing and add the forces. Next is the if statement, sphere 2.x is less than or equal to 0. We only want it to add the y component of the force of drag to our velocity for sphere 2. Go down. This next part just controls the movement of sphere 2. It's the same as sphere 1, so it's just updating the sphere 2 position for every calculation. And then this also, once the red ball hits the ground, the if statement for sphere 2's y component is less than or equal to 0, it will exit out of the loop and print sphere 2 position. Again, at the end, we are keeping up with time, This is just to keep up with the calculations. At the very end, this just sets the ground at the final calculations to show where it lands so you can judge. Alright, now we're going to run the code so we can test how it goes. Put in a mass, initial speed, a 45-degree launch angle, radius of 0.05, viscosity at 0.0125. And we're going to run it and watch it. And then we're noticing or knowing that this one does not have air drag, so it's going to go much further than our red ball with air drag in our next while loop. Shows popping out 9,183 meters approximately on no air drag. And look at our beautiful red parabolic shape. Air drag. We're getting 5,832.27. Now we're going to run it again with increased or decreased viscosity and see that viscosity plays a major role in how far our projectile will go. Now we get to watch it. See our little launch platform going off into the distance. Now they're looking very similar since there's not very much viscosity in the air, or whatever fluid that we're shooting it through. Should be air drag, right? Starting to alter paths a little bit. See what outputs we get. And we notice that the range that each of them go are very, very close together. Thank you, and that is all. Dr. Marble.